Hello everyone, welcome to our channel. I'm Alex, and I will introduce how we're listening TBM vibration to reconstruct the geological changes ahead of the tunnel. If you are interested in this topic, you can get some related knowledge about the background of this work and how we observe data from our previous videos. So let's start. The tunnel boring machine, known as TBM, is a very popular method to mine the tunnel, which is effective, less disturbing to the surrounding soil and rock, and suitable in urban areas. But when we tunnel, it is essential to know the real-time geological changes to adjust the mining progress to avoid risks, which is also called tunnel look ahead. When TBM is working, the rotating TBM machine generates strong vibrations. The vibration transmits through soil and rocks and then hits the potential obstacles and is reflected. By receiving these reflected signals, we design the seismic tunnel look ahead method. The method has advantages like small disturbance from the metallic TBM machine and non-destructive to the already built concrete tunnel wall, and without using any manually generated sources like explosive sources in the urban areas. And at last, it is very fast and easy to get and process data and don't interrupt the regular mining progress. And because of these advantages, our method is very suitable for tunnel look ahead applications in urban areas. Here we show what it would be like when TBM is working. TBM machine generates very strong noises and vibrations when it works. If you attach geophone to the side wall of the tunnel and receive these vibrations, we can get the noise recording like this. We can see apparent differences when TBM is working and not working. Compared to when TBM stops working, the vibration energy is an order stronger when TBM works. If you attach multiple geophones to the side wall, we can get this recording. This recording seems to be just noise, but actually the chaotic noise brings us a lot of information about the structures ahead of the tunnel. So how to turn this noise into some interpretable data is our biggest challenge. And in this work, we apply seismic interferometry to transform noise into some interpretable data. Here we show how seismic interferometry works in a TBM tunnel. 24 sensors are attached to the side wall of the tunnel and receive the vibration signals. In the tunnel, the sources are the working TBM at the cutter head. In the seismic profile before the seismic interferometry, for the first receiver R1, the direct arrival of the seismic wave arrives at 20 milliseconds, and the reflected signal from the obstruction comes at 50. The time shift of the first arrival and the reflection is 30 milliseconds. And then all the receiver is cross-correlated with the receiver R1, and after the seismic interferometry, all the events with the same wave path are stacked at zero time lag, and the common paths among all the receivers are removed. But still, the arrival time difference between the first arrival and the reflected wave remains as 30 milliseconds, and this procedure is equivalent of moving all the receivers to the position of the cutter head. To estimate the reflector's distance from the cutter head, we can get the time shift using the semblance calculation. As both the direct arrival and the reflected wave travels along the tunnel and share the same moving velocity, we only need to search for the event has the same slope as the first arrival. The energy is stacked in the moving time window with the slope of direct arrival, and we can pick up the peaks in the panel to estimate the reflector's distance. We tested the proposed method on field data in the densely populated urban area of Singapore. This site is located in the Jurong Formation of Singapore, which consists of various sedimentary rocks with different densities and velocities. Here are the raw recordings from the 24 geophones. If you zoom in it from 10 to 200 milliseconds, we can see many events from the cutter head's direction, and those events brings information from the geological changes ahead of the TBM. Then we apply the seismic interferometry to this recording and cross-correlate all the geophone signal with the first receiver that is most near to the cutter head. In the cross-correlation result, the event with the same wave path are stacked in zero-time lag of the profile, and that is why we can see the slope of the event at zero-time lag matches the traveling velocity of the vibration in the raw ambient noise recording. After bandpass and FK filtering, we can get the profile like this. The red dashed line marks the travel time curve for the semblance analysis. And after removing the strongest event at zero-time lag, we can see the reflections in the second profile. And all the seismic waves received by the sensors on the wall have the same traveling velocity. So we can search over the whole profile using the same travel time curve and the stacked energy in the overlapping time window of 20 milliseconds. By picking up the peaks in the semblance panel, we find 3 reflections at 30 milliseconds, 54 milliseconds, and 110 milliseconds respectively. And those are the arrival time of the seismic waves from the potential obstacles ahead of the tunnel. Although we have some nearby borehole data showing there have some geological changes from the soft and hard rock layer, but as the boreholes are quite far away from the tunnel line and the borehole number is very limited, this information from boreholes doesn't have enough resolution and accuracy. But when we project the semblance calculation result on the map, we can get a more detailed location of the soft and hard rock interfaces. Our seismic prediction result shows a potential interfaces at the ring of 668, 674, and 690, which also matches the boreholes data. And this result shows our seismic prediction result can be an important supplement to the borehole data and be an important indicator for the engineers to adjust the mining progress and reduce tunneling risks. Thank you for your attention. If you have any questions about this topic, please feel free to contact me. Thank you.